So let's continue on with this example. I've summarized the basics at the top. 3 digits, base 10, exponential notation. And I didn't explicitly write the rule here, but you remember the rule that A equals 0, E not equal to 0 is not allowed. You should simply shift the digits until you get a representable number. So let's do some examples. So there's 0.00237, so I can shift that over. It has 3 significant figures that you can see, and if I write it correctly, it's 2.37 times 10 to the negative third. That's actually 2.37 times 10 to the 1 minus 4. Remember, the e is not the exponent that appears in the power of 10. E minus 4 is what appears. So the representation, the final value of e is actually 1. And that's what we have over on the right-hand side. Now what about the number 5,632? Well, that's simply not representable. Remember, our system, our numeric system here, only has 3 digits. 3 significant figures, and 5,632 has 4 significant figures, so it's not representable. What's going to be important is to understand what's the closest representable number, and in this case it's pretty clear that since we were working in base 10, things are, when we're up in the thousands like this, things are changing in the tens digit. That's that 3rd significant figure. So we have 5,600, 5,610, 5,620, 5,630, and so on. And the closest representable number to 5,632 is 5,630. When we talk about rounding and operations, we'll see how that plays a role. Now the interesting thing is when I add 2 representable numbers, in other words 2 numbers that each have 3 digits of precision, the result may not be a number with only 3 digits. So it may not be a representable number. So 5,510 is representable, right? We can easily work that out. 122 is representable. But their exact sum is 5,632, which is not a representable number. So we're going to have to think about what are going to be the restrictions and what are users going to demand of the manufacturer of the CPU to deal with in this situation. So we're going to have somehow the ability to understand that the exact number isn't representable, and the computer is going to have to be able to round to the nearest representable number. We'll talk a little bit about that near the end of the lecture, how that's actually done. So and I guess that's what I'm saying here. All the arithmetic operations that we're going to talk about, plus, minus, subtraction, divide, and even some of the fundamental operations like square root and some of the trigonometric functions. So here we saw that adding 2 representable numbers doesn't necessarily result in a representable number. There's some issue there. A lot of arithmetic operations, either binary operations that combine 2 numbers, plus, as we see, minus, subtraction, division, multiplication, those will not necessarily result in a representative number. The trigonometric functions, even if I start with a 3-digit base 10 number, applying the cosine or sine to that will not result in a representable number. So that's going to happen all the time, all throughout our programs. And what we're going to require of the machine is that any basic operation, like I've just described, must always yield the representable number that is closest to the exact answer. It sounds impossible because it sounds like we have to know what the exact answer is. But it turns out it's going to be a little easier than that. And this is something that's a property of all the CPUs that are in all the computers that you're sitting at. They adhere to this type of accuracy. They don't get the exact answer, but they always get the closest representable number to the exact answer on those basic operations. We'll see that when we cascade or do 2 operations in a row, then things can kind of, the errors that we're accumulating can actually add constructively, and we end up that the final result is not so good. But on a single operation, this is what we'll require. So let's look a little bit more at what the numbers are. The graphic at the top, we'll see what that means in just a moment. So if we start writing down what's possible, there's actually a total of 9,100 different representable numbers. So 0 is representable. Just take 0, 0, 0, and e equals 0. is allowed. E could actually be anything, but we'll... no, E can't be anything because A equals 0 requires E to be, is not allowed to be 0. So that once we go with 0, E has to be 0. Then there's 99 numbers evenly spaced from, the spacing is 10 to the minus 6, and those are from from whatever that is to 99. And that's with A equals 0, E equals 0, B running through C running from 1 to 9, and then 0 to 9, and B running from 0 to 9. That'll give us 99 numbers there. Then when we allow A to be non-zero, we get 900 numbers evenly spaced from 1e minus 5 to 9.99e minus 5. And that's just with A and B and C running over all their combinations, but A restricted to be non-zero. Then we also get 900 numbers, just move the decimal point over 1. We get 900 numbers evenly spaced in the next chunk, and so on. And finally, the last chunk is 900 numbers from 100,000, from 100,000 to 900,000, 999,000. And those are, the spacing there is 1,000 between those numbers. So the numbers are quite far apart. So what you can see is there's a real regular pattern over most of the range. It's always 900 numbers evenly spaced from a starting point to an ending point. And that's, that happens not over the entire range, but that's over quite a large range. Then there's a little chunk at the beginning which is a little different. 0 and those 99 and then the next 900, those 1,000 numbers are actually all have exactly the same spacing between them. If you look carefully, the spacing is 10 to the minus 6th. Whereas if we looked over this regular pattern, when we were moving through that, the spacing was always changing. So again, when we look at the real way the computer does this, we're going to see exactly this same pattern. There's going to be a repeating pattern where there's a fundamental pattern that's simply getting scaled up and down. And then at the bottom end, near 0, things are a little bit different. Now the picture up above is showing that there are groups of numbers. This one, it isn't to scale. I didn't want to draw 900 numbers. I think I've drawn, looks like 8 numbers. So in the blue, in the middle, there's 8 numbers and they're evenly spaced. Then when we move to the red to the right, it's 8 more numbers and the spacing is larger but also even. When we move to the left, the spacing is smaller but also 8 numbers and also even spacing. So generally the spacing between the representable numbers is kind of proportional to how large the number is. You see that as the numbers in this long list, as the numbers get larger, the spacing gets larger. And it's roughly proportional, but the manner in which the spacing changes is very abrupt. It changes at distinct locations. So the spacing is not proportional, exactly proportional to the value you're at, but it's approximately proportional. Then the spacing abruptly changes as you move through another transition. So there's 9,100 different representable numbers. There they are repeated again. So let's have another quiz. Have we accounted for all the possible patterns? Remember that there's some illegal patterns. A equals 0 and E not 0 is an illegal pattern. And then we came up with all the other patterns on the previous page, or have we come up with all the other patterns? And if you count, you can see that we have. There's 10,000 total patterns because each of the 4 symbols can take on any one of 10 distinct values. If I just do a simple combinatorial counting problem, that gives me 10,000 combinations. We accounted for 900 illegal combinations before and 9,100 combinations that all give different numbers on the previous slide. So we've accounted for all the possible patterns. These 4 symbols, each that can take on one of 10 values, gives us 10,000 possible patterns, of which 9,100 of those represent numbers, all distinct numbers, and 900 of them represent something that we'll define later. So let's have another quiz. And you can kind of use what's written above and maybe the picture above to answer this. Let's let P be the closest representable number to the number 1 that's less than 1. So it's the largest number, representable number that is less than 1. 1 is a representable number, 1.00 times 10 to the 0. So it would be A equals 1, B equals 0, C equals 0, and E equals 4. What's the representable number that is just less than 1? And let's think about the representable number that is just greater than 1. And my question is to you, what is 1 minus p? In other words, how far is it from 1 to the representable number just below 1? And then the same question, how far is it from 1 to the next representable number just larger than 1?